So hello again. Tonight we're going to talk about long-lived deep space probes. If you remember a few months back, I did something on putting up long-lived outposts where there would be people and such. And this is maybe a little more baby step towards that. It's unmanned space probes deep out in the solar system and how you go about doing that sort of stuff and picking where you want to be and such. So this is not an official government program or proposed mission from industry. It's not NASA, European Union, Canada, China, SpaceX, none of that stuff. This is just me going, what if? Such a mission is going to be useful because you'll have a permanent observing site. How do you select where you want to put your observing instruments? How do you go about getting it done? The electrical power for it, propulsion, instruments. How long would it take to get there, wherever there is? How long would the mission be? Goal would be multi-generational, a generation being about 25 years. So you want it to last longer than the Voyagers have lasted, which is 50 plus years. And then the long term, like more than single generational term issues with funding and public attention span. If from this presentation on Broward Astronomy's YouTube channel, somebody gets the idea to do a mission like this in a government or a corporation somewhere in the planet, that would be nice. So these you might have heard of. These are probes that we sent out to the outer parts of the solar system, 2 of the Pioneer class, Pioneer 1011, 2 of the Voyagers, Voyager 1 and 2, and New Horizons. These were all ones that flew by things, took pictures, did instruments, and then just like zipped towards the outer part of the solar system. And they're never going to come back. They're never going to orbit anything. They don't have the fuel for it. And in order to get out that far in a reasonable time frame, a lot of them went around other things, like circled around planets a couple of times, went around a big planet like a Jupiter or Saturn, and then got gravitationally assisted, or as they say, slingshot out further. And then there are other probes that are in deep space, let's say deep space, but they're still in the solar system, that are radioisotope thermoelectric generator powered. These use plutonium, a particular isotope of plutonium, and the decay of the radioactive material produces a certain amount of heat. And then they use thermocouples to transfer the heat to electrons, and they carry off the electrons as a power source. And how they use ion propulsion for longer duration, accumulated acceleration propulsion to do long duration missions. The one where they tried all these things out together, the RTG, the ion propulsion, the ability for the telescope, the probe to do its own course corrections and know where it wanted to be and how to do star alignments and such, was Deep Space One. I think they had 8 different concepts that they were testing out on it. For the most part, it all went rather well. It flew by asteroid Braille, and then it flew by comet Borrelly, and then it just it's going out there, wherever out there is. And then Dawn, which is the first serious purposed probe that made use of an RTG and a ion propulsion, was Dawn, went into orbit around the asteroid Vesta and the asteroid or dwarf planet Ceres, and then it ran out of hydrazine fuel. So even though it was using ion propulsion for its long acceleration change in velocity, when it wanted to go into orbit, it needed more oomph per second, and so it had traditional chemical propulsion for that. And when it ran low on fuel, it couldn't get out of orbit from Ceres, and so it's still in a long elliptical orbit at Ceres, but money ran out even though the probe was working, and so they just shut it down. That's one of the issues with long duration probes, is attention span. So don't worry about trying to see all the various objects in this graphic in the upper left corner. That is kind of a scatter diagram, and it's of the distance. So the position in the graph from left to right is near in to farther out, and the position vertically is the duration of the orbit, how many years it is. And then the size of the circles is how big something is. So you can see some big circles there. On the left, you see Pluto. And then sort of in the middle, you see Haumea. And then over on the towards the lower right, you see Makemake. And then a bunch of other ones that just, they can't make out the names of them because the print's too small. Probes that are put into space, you'd like to put them in a good location so they do a really good job of showing you lots of stuff. The more stuff you can see from wherever you're at, the better. A flyby is not great at that. That's just a couple of things you'll see. If you orbit something now from that vantage point, you can see lots of stuff. The best orbiting thing we have for putting big, heavy things is the Earth itself. That's our Earth-based observatory. But it's not best because they have to look through the atmosphere. So we put probes into Earth orbit, like the Hubble Space Telescope. It's above the atmosphere, but it's orbiting the Earth about every 90 minutes. So it's got to deal with daylight and dark, and the sun gets in the way. But then when we put things out at the Sun-Earth Lagrange point 2 or L2, that's better because now they can be always facing away from the sun, the Earth, and the moon, and it's darker out there. So that's where you found Gaia, who's now in solar orbit, and the James Webb Space Telescope, or JWST. Some people will say, put it on the far side of the moon. Well, the far side of the moon is not the dark side of the moon. The far side of the moon, when it's a new moon from Earth's perspective, it's a full moon from the far side of the moon's perspective. So L2 is still better because no sun. The idea is to get farther away from the sun's interference, the solar wind, particles and things like that, and to get away from the asteroid belt, from debris fields and such, and just get as far as you can out in the solar system. So why not orbit a large planet like Jupiter, Saturn, Uranus, and Neptune, or a moon of a large planet? And the answer is too much interference, reflection off of a large reflective body like Jupiter, or radiation from Jupiter's radiation belts, their magnetic fields. Not a good idea there. Well, we've been to Pluto. Let's go back out to Pluto. Pluto has a somewhat large moon that Pluto and the moon Charon are actually an orbital pair, and the orbit is actually between the two, not on, one is going around the other, but they orbit as a rotating pair, and that makes the orbit very complex. As we found out, Pluto has 7 moons now, so there may be even more, and that's too many targets that you might accidentally run into. So let's find something that has no moons or fewer moons. So if you go out further, you're going to be in the Kuiper Belt, or parts of it are referred to as the scattered disk of the Kuiper Belt, and that's where you find the things that are elongated orbits, not nice, more circular orbits. We want a body that's large enough so it's attained hydrostatic equilibrium, or it's basically spherical. And that means that if you want to orbit it, the orbit is going to be less chaotic. If you want to orbit something that looks like a potato or something that looks like a dumbbell, your orbit is not going to be simply an ellipse or a circle. It's going to be a sagitt. And that's difficult for us to communicate with from Earth because a lot of times it is behind the object. Don't want one of those, want it large enough to be somewhat spherical or semi-spherical. You want it large enough that it's cleared out most of the debris field, so you don't want a body in the asteroid belt. And if it's in the Kuiper Belt, you want something that's not too ingrained into the denser part of the Kuiper Belt. You want something that is out from it. And once you get to orbit there, you want to put it in what is known as a sun to body supersynchronous orbit, which means it'll orbit. If you're the Earth and you're looking out towards it for radio communication, you want the orbit to be going around the body this way, not this way, because if you do it that way, now you've got time when the probe is behind the planet or the asteroid. You want it orbiting this way, so it's always able to face the Earth, and so that the instruments are always able to face out in space. So here's how you pick what you're going to orbit. You have to understand the orbital parameters, and this is a lot of ellipses, very few true circles. And what you see here is the stuff that's like Pluto, Haumea, Makemake, Eris, and then the bigger planets like Saturn, Jupiter, Uranus, and Neptune. And you'll see that the bigger stuff is sort of compressed into the disk of the solar system. But then you've got these wide elliptical things, and Eris, number 557, is one of those things. And if you look on the right, if you took that picture on the left and you flattened it, and you looked at it from overhead, which orbit is the most elongated, can get you out further away from all the noise of the solar system, and also off shifted from the center of the solar system. You see the sun is on the left, and the other focus of the ellipse would be on the right, and it's not in the center, and that's Eris. So Eris is not only tilted up, tilted over slightly, but it's also slipped to one side, which means you're going to have a very elongated orbit. If you put a probe in orbit around Eris, it's going to get a free ride courtesy of Eris out to a very distant part of the solar system, so you can look out into deeper space more easily. And since it has a free ride of a couple of 100 years around Eris, once you get it out there and it's working, if you can still communicate with it, you can still observe with it so long as the instruments work. So at the moment, Eris is the best candidate we have. It's got all the right orbital parameters. So what kind of instruments will we put out there? Well, remember, this is going to be multi-generational. You won't have any opportunities to go out there and do any work on it or upgrade. So unless it's a software update, it is what you launch. But you never know in advance what you're going to want to observe. So instead of it being just infrared only or something of that nature, you want it to be kind of like the Hubble Space Telescope on steroids. You want radio, radar, infrared, visible, ultraviolet, maybe also throw in some X-ray or gamma, or maybe even, if you can make it small enough, a gravitational wave observatory. There's no single instrument that should be the design governing factor. It's more a matter of opportunistic. It's because the probe is out there. What would you like to use to observe things that you don't know what you're going to be observing in advance? No single instrument should be the best possible. All instruments should be the most capable you can while still putting them all on the same probe. Use it as your first look. When it finds something and you go, hey, that'd be interesting to get a higher resolution image or a better radar image or whatever, then you hand that off to James Webb Space Telescope, Hubble Space Telescope, ground-based radar and radio astronomy. I know that's a picture of Hubble. Or is it a KH-11? Who knows? But it has solar panels on it. It has a little tiny dish antenna because it's in orbit around the Earth. That's just the design of it. And the flap on the front is because, remember, as the Hubble goes around the Earth, it'll be in sunlight for half of that orbit. So they have to close the front down. And communicating with this thing, we already know from the Voyagers that it can take many days for one-way communication with the Voyagers. 20 some odd days, I think it is now. You're going to need multiple bands for backup and alternates. For imaging high-speed data, you want X and Ka. And then for just the low speed, are you working okay? Here's a command. What's the telemetry? Lower frequency S band for being able to communicate through more interstellar noise. You probably want multiple antennas, a dedicated antenna for each band, but radio communication might not be sufficient. And you probably want to add laser communication as we have nowadays. There are 3 NASA Deep Space Network communication sites on Earth, and we probably aren't going to add any more sites or any more dish antennas, but you probably can dedicate transceiver channels to whatever the deep space probe is so that you don't have conflicts between signaling. But you might even put in Earth orbiting deep space network antennas because that way the signal might be improved because the DSN station would be in orbit above the Earth's atmosphere. Now, because it's so far away and it takes so long to do things, you probably want the probe to have some smarts. Some might say AI, but some procedural smarts. So it should know how, if you tell it, here's the coordinates for something, go find it and track it and stay on target with it and do this kind of observation with these instruments for this long, stack this many images, go. And you send that program out to the probe, and then the probe does its job. And then maybe if you're doing stitching, putting together a pattern of images, it'll stitch them together, align them, do the average stacking, and then send you back the result, which means you're going to need to store a lot more data on the probe. And since it takes so long to send and receive the data, you probably want to piggyback where you can say, well, I'm going to take the next week to send data back from last month's efforts. And at the same time, I'm receiving the current program for this month's efforts, so even more storage is required. So how would you get it out there? You don't necessarily want to invent some new rocket or use something that's not yet proven, like Starship and Super Heavy. Probably going to be something like a Falcon Heavy, maybe in the future a Super Heavy, but probably Falcon Heavy initially. And all you're going to do is get it out as fast as you can beyond the Earth. And then maybe you'll do some flybys. Maybe you'll do a flyby of a big Jovian planet like Jupiter. You're going to need something that will do the chase or catch-up velocity, as they say, delta V, to get it there and to orbit it. And so whatever velocity it has coming away from Earth, plus some flybys, and then you want to kick in the RTG-powered ion propulsion to constantly accelerate to improve your delta V to get you to the target. There'll be a one-time use of something like Hydrazine to rapidly slow it down to get it into orbit gently without having to go through reentry plasma and heat shields and things like that. Once you have it in orbit, you can probably use ion on or inertial to adjust it for observing things. So what kind of orbit once you get there? Whatever the celestial body is, let's say it's Eris. So it's Eris sun synchronous orbit. Fear of the body, and then you're going to be orbiting around the outside of it, and you're going to be in an orbit that's large enough so that if the object is rotating, it rotates slower than your orbital speed. So if you want to do a survey of the body that you're orbiting as an initial test of the probe, you can do that. Since it's going to be out towards the far end of the solar system, the larger planets will come between Earth and that. But the larger planets, even though they're moving slower in their orbit around the sun than the Earth is, that object will be so far out in the solar system that Jupiter will fly by in a matter of a couple of hours. So you might lose contact with it for a couple of hours, but it's not going to be for an extended period of time. So let's talk about the longevity issues. Let's start out with, it's going to be multi-generational, multi-hundred year. Eris, or as a backup maybe Sedna. Power source and fuel supplies. You're way too far from the sun for solar panels. You're going to have to use RTG. But here's a little something you don't know about RTG. The Voyagers, which are powered by an isotope of plutonium, their power source is good for about 87 years. That's the half-life of that particular isotope. And once it achieves half-life, the amount of heat it puts out is about 1/2 of what it did when it left the Earth. So we're at 50 plus years. When it gets to be 70 years, the Voyagers are not going to have enough power to do much of anything, and they'll probably shut them down. Plutonium-238 gives you about 0.57 watts per gram of material. If you want to extend that out and say, I need a material that has a slower decay rate, Americium-241 has a half-life of 240 years. That sounds right. That's what we want. But it produces reduced heat. It's only 0.11 watts per gram. So you're going to need about 6 times the fuel mass on launch as the Voyagers had in order to power it for those 240 years. Or maybe 3 times if you only want to make it last for 120 years. I'd say if you're going to launch it. Do the 240. And we'd obviously use ion propulsion, but xenon fuel is expensive and you can only compress it into so small a space because it's the heaviest ionized particle you can accelerate. So you might want to pick something that maybe costs less. You can have a bigger tank of it, like argon, which is what SpaceX has gone to. They went xenon, krypton, now they're using argon. It's cheaper and longer fuel supply. It'll need hydrazine for its orbital insertion, fixed fuel supply, and the hydrazine, as the tank starts to diminish, needs helium in order to pressurize the hydrazine to get it to go out the nozzle. If it's going to take you a while to create the probe, consider radiation reflection pressure as your replacement for ion propulsion. Power is the fuel. Long-lived power means longer-lived fuel. And then you have to cool the instruments. Liquid nitrogen, liquid helium. The James Webb Space Telescope and the Roman telescope use what is known as recycling. So they actually keep cooling the liquid helium by doing it electronically, and with pumps, they can pump it back down to a lower temperature when they're not observing, because otherwise it vibrates the whole spacecraft. But when they pump it back down, they get extended life off of the helium coolant. And now the greatest threat to mission longevity, especially ones that are multi-generational. People will often say, why are we doing that stuff out in space? We've got our problems here on Earth. Let's shift the budget money. And from time to time, the budget money shifts back and forth. It's an elastic process. If it shifts away and you're going to come back 10 years from now and put out a new probe, then it's harmful but not catastrophic. But if you get a probe way out there and you shut it down and you lose communication with it, then you need to get some fledgling funding always there to keep up with it, to know what's going on with it. Even if you say, well, we're not doing any science anymore with it, well, at least we're keeping in contact with it. You can do that. But as has been recently discovered, they outsource that. So NASA outsources operation of the Jet Propulsion Laboratory to a university system in California. But now they're thinking about maybe somebody else will do that for less money or whatever. And the Space Telescope Science Institute, once you flip these contracts around, it's real difficult to keep the skilled labor in place to maintain what you had. Here's an example of what happens when you don't maintain things and you don't improve things. Arecibo, you can look it up. And then there's the General Administration of Science Missions. If it's a science mission, it's not the NASA program scientists, it's U.S. scientists worldwide that say, hey, I'd like to use some time on the Hubble or the JWST or some other probe. They submit an observing request and it goes into a queue. it gets reviewed by a science team, and then they go, okay, we've approved your observing request for this date time slot with these instruments on this probe. And then your observation gets executed. Capture the data, do raw data recording, and then you post-process it, disseminate the information to the science team, and then there's long-term archiving, like the MAST archive out of Space Telescope Science Institute, for sometime later. You don't need a new probe. You're just going to go back and review older data using newer software or AI, and you find things. And then how do you get those new discoveries published to the public? And that's, you need somebody to publicly promote it. So the two pictures at the bottom that's the Mission Control Center from the Apollo program. It's now a museum. And then you have the U.S. House of Representatives. No members present, but this is the U.S. House of Representatives. That's where the funding's approved. So if you want to take the thing on the left and have people there, you need the thing on the right to have people in it that are willing to fund the thing on the left. It's hard enough to do that on short-lived missions that might be 5 or 10 years long. Imagine trying to do that when the representative's lifespan is shorter than the mission duration. So in summary, we've sent probes on multiple decades-long missions out into the outer part of the solar system, the Pioneers, the Voyagers, New Horizons. And once we sling them out there, they're just a flyby. They might go by a couple of targets, but then they become useless for further object observing. They're just happenstance observing whatever they encounter, like interstellar winds and such. If we move it to an object that's farther out in the solar system and then we orbit it, that will give us a more multi-generational probe. The probe technologies that, if we started right now, are pretty easy. They're things we know, ion drive, RTGs and such. We have the math to do slingshots. We do it all the time. We need to select something that has the right path that we can catch up with it. If we wanted to do something like Eris, we know the year duration of Eris. We don't know its orbital speed. We don't know how fast it rotates, so we won't be able to put it into the correct orbit until we get closer to it and can start doing some en-route observing. But we know we want it in a sun-synchronous orbit, so it faces the Earth most of the time and faces out into space all the time. And you want the orbit to be large enough that it's longer than 1 day rotation. And it'd be nice if you could observe out into the universe, but also observe the body that you're orbiting to get new data. And you want instruments that cover the entire spectrum. You're only going to get one chance at this. So no big of any instrument, just good of all instruments. Radio, radar, infrared, visible, UV, etc. Whatever we can put there. When we launch it, it might take a decade for it to get there, but you can expect it to last for centuries. Eris is 200 plus years in orbit around the sun. Design and plan accordingly. But if you need to have a name for this particular program, the Eris Orbiter Universe Observing Mission, chock full of words, like NASA programs usually start out that, and then they come up with a catchy acronym or shorten it or name it after someone later. And the links to lots of probes and objects and such. Comments, questions?
Very interesting.
Yeah, I think that, I went from we're going to put an outpost out there with people. People are going to make the price of it very high. What if we go the other direction and say, instead of putting something out there that requires people to periodically go out to it, what if we put something even further out with more instrumentation and it goes on longer than lifespans? And that's what you really want, because if you want to get a better look at something that's further out, you're not putting it a light year out. You're putting it out maybe half a light year, but you're putting it so far away from all of the interference of the inner solar system that you should be able to observe better, even if your instruments are not as grandiose.
I wonder if our society has the patience to wait for these things. They'll shoot something out and go wait 20 years. Maybe they don't care anymore.
Well, that was one of the issues with New Horizons. New Horizons was launched, and then you heard nothing about it for about 10 years, because that's how long it took to get to Pluto. And once it got to Pluto, you're good for maybe a better part of a month as it approaches, takes images, and then curves around and flies around. And then you go silent again for another 16 months. And then you say, hey, look, we just passed this one object. Well, how soon are you going to see another object? Oh, about 6 years. What? And then in the budget from last year, NASA was going to zero out New Horizons. And they found another object that they could go do some observing on. as they do another flyby, and yeah, okay, we'll give you a little money. So
it's not just always the money, it's the temperament of the people.
Well, yeah, I think it's both of those things. The number of very long to develop, very long lasting projects that the human species has attempted and been successful at and sustained, I guess you could count on the fingers of one hand. Think of things like the Hoover Dam. The Hoover Dam didn't take all that long to build because we put a lot of effort into it. But once it was built, it provided power and water for decades. But now that the tank is draining, and if it drains down any lower, it won't be able to produce power with it. It'll become basically a museum piece. Are we doing anything to build like anything to improve it? Well, we drilled a hole out the bottom and we went down and we got the last of these soda straw sippings from the water below the base of the pool. And once that runs out, we're done. And they're just going to write it off. Like, what? Why don't you, drill a pipeline in from the Pacific Ocean and build desalinization plants at the north end of the Colorado River and drive the tank full again, and then take the salt and ship it off to the salt flats where it won't be any different, because that's the salt that's there already, is ocean water drying up. So yeah, we could do those kinds of things. Oh, but it would cost billions of dollars. If the right companies are making the billions, we apparently don't care about that. But if it's to solve a problem where we don't want that problem actually solved because there's a lot of money on the line for the next guy coming up to create like something that costs more but does less, it is more about the willingness to do it and the politics of it than it is about the technology of it. So who knew that Eris was the item in our solar system that we're aware of at this point that had the greatest elongation, greatest orbital tilt inclination, and a long, like 82 AU distance from the sun?
That how far it is?
That's 82 times 93 million.
Yeah,
that's how far it is from the sun. It's way out there. It's a few billion miles out there.
That's amazing.
Yeah, but we can see it from Earth.
It's amazing that we can calculate that and figure it out.
Oh, we do it with parallax. So if it's the old eye trick where you close one eye and then you close the other eye and you stare at something. The angle between the two is a triangle. And we have the trigonometry to measure the distance based upon the angles. When we're on this side of the sun, we take a look at it. And then when we're on this side of the sun, we take a look at it. And the angle difference against the background of space tells you how far away it is. And it's good for, maybe it's off by about 12%, but it's in the ballpark.
Your thought of orbiting it, and that would be a great free ride, as you say, way out.
Oh yeah, once you're in orbit about it, and if you're in a super geosynchronous orbit, you're going to be in orbit for hundreds of years. There's no orbital decay. And if you're in orbit that's super geosynchronous, the planet will actually rotate slowly beneath you. So if you want to observe Eris, fine. If you want to observe things further out into the universe, you're on an excellent path, because you can actually get above the plane of the solar system and look down towards the planet and see the whole solar system there. So it's a really good observing location for an observatory. We just need to create the will to do it. Now, I mentioned ketchup, and I don't mean the seasoning, the thing that you put on your burger. Catching up as in when Eris is close to the Earth is when it's traveling its fastest. It's doing its whip around the sun. When it's out farthest from the Earth is when it's traveling slowest in its orbit. Perihelion, aphelion. The point at which it's slow enough that we could catch up with it is when it's farthest from us. And it might take 30 years for us to get there at our slowpoke rate. But when it's close enough to us to make it where we can get there within 10 years, now it's going zip past so fast, we need to catch up with it. So we need a good oomph of propulsion from the launch vehicle, and then from maybe some gravitational slingshotting, and then ion propulsion that might be on for 2 years to get it to go fast enough. But then once we get there, we need a rapid slowdown by hydrazine propulsion in order to slow it down without requiring it to go through like a plasma shock reentry and need a heat shield and all that kinds of garbage. So yeah, orbital mechanics. But I thought it'd be a fun topic to get out in the public arena of Broward Astronomy's YouTube channel, see what people have to say about it. Any other comments or questions? I'll stop recording. Hearing nothing.